This program is brought to you by Stanford University. Please visit us at stanford.edu.
Okay, so I'm going to commit the first sin, which is PowerPoint, but it's a crutch I use to remember what I'm supposed to be talking about, and so I'll do that. I got to let some air out of the tires first. I don't really know much about teaching. I really don't. I know a lot about thermodynamics, okay, but I don't know a lot about teaching. I think I'll make observations about things that I've learned and try to share those, and I think that may be of use. But a lot of them will probably be rather obvious to people who really do know about the process of teaching and how to do that rigorously, Michelle and Robin and those who have studied it much more seriously. So what I'm going to try to do is tell you things that have surprised me as I've gone along and that I think have been useful applying it in the classroom. First thing to start with is teaching difficult subjects. The difficult is in quotes. And the reason why it's in quotes is I've never thought that thermo was a difficult subject. It wasn't difficult for me when I was a sophomore. In fact, I walked into the class and I said, wow, this is the most obvious subject I've ever seen. Energy's conserved. It tends to disperse. Things become more random. You can build really cool stuff. You can fly airplanes. You can build cars. You can go zoom, make flames, all kinds of stuff. And so it really was a very intuitive subject. I also haven't found it to be difficult to teach. Although I did get that advice when I first got here. Someone said, well, we're going to put you in teaching E30, and the undergrads, it'd be nice if we could start you with graduate thermo. The undergrads are going to eat you alive on this one because at least half of them are going to hate the subject, and you're going to pay the price for it. But I didn't find that to be the case, and so I don't quite know why that is. But I'll try to give you some insights that I've sort of figured out along the way. So some observations from teaching thermo to sophomores, seniors, and graduate students, and I really have enjoyed that. I mean, I love the subject, I love teaching, but I really love each age level too. And what you're trying to do are different at each one of those levels, and it's special, and it's neat, and it's how to move them along. It's a lot like raising kids, right? They're special at each age, and they have different requirements as you go. Okay, so moving along. Life is a path function. For the little thermo contingent in the back, you'll know that one of the concepts that's sometimes difficult for people in thermo class are exact and inexact differentials, path functions, and state functions. So this is a bad pun, and I have lots of bad humor that shows up in class all the time. I take the hits from the bad humor from the students. Life is a path function. Okay? Point function is about the beginning and the end. You begin life, you end life. That's not so interesting, right? The quality of life is a path function. It's the path that you take from the beginning to the end, the integral of that path. That's the special part. That's the inexact differential. That's where the choices are. And that path is hugely important, not just in thermodynamics where we use it for a whole bunch of different things, but it's important in teaching. So using the path that you've come along to your advantage in teaching and helping to explain and communicate with people is a huge thing. So recognize that you all bring a special path to it, and it's not the same as anybody else's path. So I'll tell you a little bit about my path, and maybe it'll show where it comes out at some point. Where am I from? I'm a local boy, as Michelle had said. So I went to St. Simon's in Los Altos, then St. Francis in Mountain View, then Santa Clara in Santa Clara. First public school I ever hit was Berkeley. Boy, what a shocker that was, getting to Berkeley. But I saw a lot of really good teaching along the way. Particularly at Santa Clara. In fact, the teaching bug. So I like to think of it as you get the teaching bug somewhere along the way. You're not quite sure where you get it, but it's that little thing in the back of your mind that says, maybe I want to teach. I got the teaching bug when I was at Santa Clara. I had a number of professors who were really good at explaining things. Among them, some professors who taught me thermo, heat transfer, other subjects that were considered to be difficult. I saw a couple of examples that really weren't good. And for the most part, I could see why they weren't good, what was missing. And I sort of saved those as I went along. When I got to Cal, it really was a little different. Now, part of the shift was going to graduate education, which really has a different set of objectives than undergraduate education. But part of it, too, is I'd gone from a school where the focus was teaching, okay, and clarifying and explaining. That really was the primary duty, to a school where the focus was research. And in many ways, the undergrads were kind of, and so it was out there, but wasn't always that well explained. On the flip side, though, I also realized something that was kind of important for me, too, and that was that I didn't need so much help as a graduate student. Okay, that I could look at it, and as long as it was articulated well and precisely enough, I could fill in all the interstitial spaces, and that was fine. And so bearing in mind the different objectives at different levels was an important thing. But I definitely got the bug from seeing some really good teachers when I was an undergraduate, no doubt about it. Real world experience. So Michelle mentioned that I didn't do the straight through thing, even though I pretty much knew by the time I was a junior as an undergrad that I was going to go to graduate school. And a big part of that was, maybe I could teach. I was good at explaining things to my fellow students, and that was sort of one of the criteria. I really liked the subject matter. I couldn't get enough of the subject matter. But by the time I finished Cal, I was 25, and if you take the beard off, really baby face, and the average age in my lab was 29 years old, and it just did not seem like such a good thing. I was likely to be younger than most of my graduate students. And so it seemed like a good idea not to take academic offers. I did academic interviews, but I chose to go to the national labs because they were a really special place at the time. A place you could do just world-class research. You had resources like you wouldn't believe. The resources that I had for writing a paragraph or 2 paragraphs were more than my advisor, world-renowned Tony Oppenheim at Berkeley, had. And I would have to write a page or half a page to get those resources. So it really was a phenomenal place. And it was a reversible path. There's a thermodynamic pun in there too, for those of you who are thermo folks, in that you could go to the national labs, do that level of research, and go back to academia because it was published work. So it wasn't in classified stuff, it was in energy stuff on the outside. And so it made for a path where I knew I could go back and finish the objective of wanting to teach and do research. But the other thing that was really important about it was a whole other set of experiences. One can argue about whether the national labs are in fact the real world. Okay? But if you look at companies too, they're all different. From the large company model to the small startup company model, they're all over the place. Fact is, all of this is real world. What we're doing here is real world, that's real world. It's all about the human beings who make these things happen. But having some other set of experiences that broadens it really does make your life richer. Why return? I wanted to teach. So I was there for 10 years. I remember telling the boss I would be there for 4 years. Okay? And that was because I'd done everything in 4-year quanta. Yeah. High school, college, graduate school, everything was 4 years. So of course I'd be at Sandia for 4 years and then I'd leave. But I got married and had kids and a whole bunch of other things happened. So it was actually 10 years before doing it. But the reason for returning was that I wanted to teach. I mean, research is great fun, okay? But it's sort of the tip of the spear, right? It's figuring out new stuff, but the number of people that you get to talk to about the new stuff, if there's 10 people around the world that you can have a really good conversation with about it, you're lucky if it's 10. On the other hand, if you're teaching a PhD level class, there may be 10 students just in that class who want to know about it. If it's an MS class, there may be 25 students who are ready for that. And if you work your way down to a sophomore freshman class, there may be 100 students that you have an impact. It's a much smaller impact, but a much bigger base. More people, and they'll go out and affect other people as you go. So there's the chance to have this huge spectrum from new knowledge, small people, delta function over here, to really broad sort of distribution. And that's the really exciting thing to me. So that's sort of my path. Teaching thermo at Stanford. One of the things I've really liked was to be able to go from E30, so intro thermo for sophomores, to ME140, more advanced thermo. I won't say it's advanced thermo, it's just more advanced thermo for juniors and seniors, to ME370B, which is part of a graduate sequence at the MS level, which is modeling an advanced concept for MS students. And so it's great fun to kind of work across that spectrum. But one of the most important things that I've come to realize, and it's taken a while, and again, this may be obvious to the pros, is that for each one of these classes, besides the things that are nominally part of the class, there's another objective. And it goes with the age of the students. So when you're talking about E30, we're talking about intro thermo. We're talking about the first law. We're talking about the second law. We're talking about state principles. But there's an almost as big objective, which is an introduction to the analytical side of engineering. Most of the students who come into that class have been through sort of the physics track of go in and look at what's happening in the physical world, find the governing equation, put the things into it, and obtain an observation. Engineering analysis is about going into a space and doing it systematically enough that you can now modify the world around you to purpose, which means you've got to own that piece of the space in a very, very systematic way. Forwards, backwards, sideways, limits of assumptions, all that together. And it has to be done with a formalism so that you can extend it to increasingly complex systems. That's the beginning of engineering analysis. And you've got to start people with that as sophomores or even freshmen. if you possibly could. So for a lot of the students coming into the class, that's the really big challenge. They've heard of the first law, they've heard of the second law, but they're not systematic in how they work. So that's one of the key things. ME 140, so E30 for MEs is sort of the entrance to thermal science, to the more analytical side of what we do. ME 140 is the back end, it's the capstone. So between the two, maybe in the winter you take E30 as a sophomore, then you take fluid mechanics in the spring, and then in your junior year, heat transfer, compressible flow, and ME 140, it's the last class. E30 is the entry, ME 140 is the end. So the objectives are really different. So it's more advanced thermo. We pick up chemical thermodynamics and phase equilibrium and mixtures and stuff like that. The stuff that we didn't cover in E30. But the second part's really the big part. For people who ask, what's the class about? It's 25% about thermodynamics, and it's 75% about making the transition from a student view of the world to an engineer's view of the world. From a view where you had these well-posed problems in the back of a book with no extraneous information that you could solve on a green pad, to a gas turbine engine. Is it good or is it not? Should I invest? Should I not? Reverse engineer. Okay? And so the take that you have is very, very different. You don't want the students coming in and saying, I can't solve it. What you want to do to work the students too is to come in your office and say, okay, I'm having a problem with this, but this is what I'm thinking. I'm thinking that if we do this and we do that, it means that. But if that's the case, then, but I could go back to the lab and I could measure. Okay, fine. And they walk out. That's what the engineer does with the problem, not punt. So I can't solve it. I'm stuck. And that's a critical component of the class because of the age that the students are at. Okay, it's got to be that level. And the place where the class came from, quite frankly, when I first got here, I noticed that there was a big disparity. There was a personal disparity between what I assumed and expected from new master's students who were joining my group and what we were delivering at the end of our undergraduate program. That a student would come in and I'd say, well, you know, why don't you write a code that will figure out what the efficiency of this thing is? And they go, yeah, write a code? Heating value? Chemical thermo? Huh? And I looked at our curriculum and said, oh, you know, we never actually asked them to do that. And we never actually asked them to go out to the laboratory and to check it and to reverse engineer something, to figure out the efficiency of the component, to obtain a critical judgment, to integrate writing the software, putting all the properties in to get real answers with real data for real problems. And that's where ME 140 came from. Okay? Because that heavy end was making that transition. And that's worked rather well. 370B, the MS level, its secondary objective, master's students already know a lot. They know a tremendous amount. They've already seen all the cool stuff. So in E30, explaining how the jet engine on the wing of your airplane works is, wow. You know, they fly home for Christmas and they're looking at that engine and say, okay, that's the fan, that's the output shroud, and that cone in the middle, and that's the small part of the thrust, and that's the compressor, that's the combustor, and that's the turbine. Oh, that's pretty cool. By the time you get to the MS level, they've seen all that stuff. There's no more cool in this is how the jet engine works. The cool comes from this is how the state-of-the-art GE H-system power plant works. And if you write the code, you'll get those numbers. And if you modify that, you could argue with the people in the GE systems group about how to improve it. That's the level that you got to get them to. And they have to have the tools, the understanding, and the model problems to integrate those with the confidence so that when they're listening to somebody at a GCEP conference who says, you know, we can do this, I don't know that you can do that. How are you going to do that? You know, what's your regenerator effectiveness? How did you get around the problem of this? And it's a legitimate question. It's not somebody saying, oh, I have a little observation. It's a legitimate question for interacting with the energy world. But that's where they have to be, is to know that they have real answers. So it's a different objective. But all of those are underlying the classes. And my guess is that for all the classes we teach here, unless it's a purely elective class, there's probably a secondary objective out there. Okay? Sometimes it's hard for us to realize. It's been hard for me to realize at times. Okay, so in my simple way of thinking, when I think about classes, I think about 4 key elements to the class. What are the concepts? What are the tools? Examples and experiences, maybe they couple together, maybe they're two distinct things. Concepts. In a class like E30, it's first law, it's second law, and it's state. Relatively simple concepts. In ME 140, it's chemical equilibrium and phase equilibrium and mixtures. It's how do you do the reactive part of the world. In energy systems, it's complex mixers, it's exergy, how you manage resources, It's ionic liquids. It's all the stuff that's really hard and nitty-gritty, but they're ready to do it and do it quantitatively because it's important in the world of energy. It's surface interactions, all the things that were a little too hard to do at some point previously. Tools. So the concepts are the part that I think anybody who teaches the class is going to cover the concepts, right? They never change. They're the fundamentals. They're the principles. The tools are always changing. And that's a really important thing, is to separate your tools from your concepts. Okay? Oftentimes we forget to do that, and we teach the tools too much, and the concepts kind of lag, you know, and so we've got to be really careful. So tools, when you have a class like E30, you're trying to get on top of being systematic and figure out how to do the analysis. The tools have to be simple. It's tables, it's a methodology for analyzing the system, putting boundaries around, identifying transfers, writing balance equations in a really systematic way. But you can't ask them for more than that, because those are the tools that they have to have in place to begin to do it. So it's a simple set of tools, but it's the right set of tools for sophomores to use. When you get to ME140, you've now gone more than a year of heavy lifting, really heavy lifting, big ramp in the intellectual growth. So now the set of tools have got to move up. It can't be problems on green pads coming out of the back of the book. The problems have to come out of the laboratory. Go in, run the jet engine, measure all the states, reverse engineer that. How am I going to get real numbers for that? You're going to put in real properties. How am I going to do that? You're going to write code. Why am I going to do that? That's how we really solve problems. If we ever get a green pad problem, we say, oh, look, I got a textbook problem. Woohoo, that's fun. But in the real world, we don't solve problems that way. But making the transition to an engineer's view, you got to make that transition to the real world problems. And so it's a different set of tools, but it's the set of tools that allows them to engage where they have to engage. If I asked people at the end of the thermal science track to do E30 problems for homework, they would hate the class because they're so underutilized. It would be a form of disrespect on my part to ask them to do that. Just a bad idea. Now, of course, they'd say, sure, 15 hours a week versus 6. You know, what's the choice? Yeah, but you got to stretch them, and they will see the benefit from it. They absolutely do, my opinion. 370B, the tools have to move up again. So it's no longer sort of the first writing of code and how do you solve these problems and match with the real world. Now it's, you know, okay, you know how to write the code. We can bring other tools in that will help you. So you don't have to write every piece of code for every property and every form of solution, equilibrium solvers, blah, blah, blah. You bring in the pieces you need, and you bring in the new concepts as the problems dictate. That's really important, is the link between the concepts and the tools, because one of the objectives here is when you walk out, you will not have seen every concept you will ever need to do the world's energy systems. But you better have seen enough things that surprise you that you can now say, okay, I'm going to do that system. It requires this concept. I will go and get the concept. I will build the tool or find the tool. I will integrate and I will do it. I will not be stopped. That's one of the key things you need at that master's level to engage the world. And so it's a different set of tools. Examples and experiences. So concepts are great, got to be there. Tools allow you to engage the concepts and do something with them. Examples and experiences, that's the kids' view of the class. This is where the class is for them. It's the homework you give them every week. And it's the examples in class, but even more so, it's the homeworks that they have. E30, they've got to be things that are compelling. Third week of class, we do auto cycles and talk about gasoline engines and how they run. The message from that is, after 3-week investment in thermodynamics, I can tell you why you want a high compression ratio engine. And we can have a conversation that's a significant conversation because you already know a lot more than you thought you knew. And you work your way from there through refrigerators, through jet engines, through all kinds of systems as you go. ME140, that's the place where you got to be running jet engines. You got to be running fuel cells. You got to be building rocket motors and firing them off. Because that's the only way that you get over that transition of, well, I can analyze it, but does it really work that way? Yeah, it really does work that way. And you can really build that. And so they have to become much more physical examples. When you get to the master's level, though, they've already had a bunch of physical examples. So they're ready to be a little more distant. Plus, it's a little harder. You can't really bring power plants other than cogen, in here. And you certainly can't build them over the course of the quarter. But they also don't quite need that. They have the confidence. They're pretty good engineers already. Now they want to see, okay, how do I extend beyond? Have I got the real answers numerically as you go? So you set examples from the real world of energy and from innovations on the real world that say, okay, this is where the world of energy is. Build your model of cardinal cogen. Wow, that gave me the power out of the turbine, the same one they had when we went on the tour. Wow, I got the steam power out of that. Okay, what happens if you reroute the steam? Can you make a better plant than they have over there? Oh yeah, hey, I could make that a better plant. And when I did the analysis before, I got the real numbers. I could believe my numbers. Hey, cogen guys, I got an idea for you. That's what I'm looking for. Okay, so important. I just got a couple of panels of observations with various titles. So here's Edwards' platitudes. Never teach a subject that doesn't excite you. Now, there's not a lot of subjects in mechanical engineering that don't excite me, but I was thinking hard about one. I would never teach a class in convection, a graduate class in convection. And the reason is not that it's not important, because it is important, but it's still largely stuck in sort of a 1960s correlation-based style of engineering, which is necessary to get results, but it really doesn't fire the mind. And until that transitions, it would be a subject I wouldn't teach as a standalone subject. For sure, I would teach it in a class on heat transfer, which I would love to do. But I would set it as a highly empirical subject that's just waiting for some really good stuff, really out of turbulence. You need that first to move significantly before you can do it. But there's almost nothing else that I wouldn't want to teach. But you've got to be excited about what you teach. Never try to teach in someone else's style. So this is sort of back to the life as a path function. I have a schmaltzy, punish kind of style that I would never suggest anybody try to emulate. It would just be a bad idea. I know some other people who have incredible styles, who have styles that are just, fantastic for graduate students, that just, highly analytical subjects, works really, really well, works terribly with sophomores. Your style has to be your own. And I've seen a lot of people who will say, well, gee, I'm going to do that thing that you do, in my class, and it's probably not going to work. The example might work, okay? But the examples really should come from your life, not from somebody else's life. Pick examples that fire your mind as you go. But I would never try to imitate somebody else's style. Never waste the student's time. Never fill time. If there's some reason why you think you're filling time or doing something, stop and think about the syllabus. Think about where you're at and try to restructure this somehow. I mean, you have very little time. I plan the classes according to, okay, how many assignments do we have? What are they going to do? How do I get them there so that they're ready to do it? Because that really is their experience. Where they put their time is their experience of the class. It's not listening to me in lecture. It's them engaging the problem sets. Never give them something artificial. Give them something you believe is really a good problem and is worthwhile. If you ever have to, for a pedagogical reason, and I would suggest that you avoid this, but if you ever do, own up to it immediately. Say, okay, now I'm going to give you this, and you see this piece over here? Now that's going to seem a little artificial to you. Let me have that one. There's a way that I can fix that, but that's going to make it much harder. But what I'm after is this piece over here. Okay, so spot me that one now. And if you want to know how to do it the real way, I'll show you how to do it the real way, but it'll triple the work. So that's why I'm pinning this problem here. But students, they'll smell that, right? And then they lose trust with what you're asking them to do. No excuse for being boring, which I probably shouldn't put up because I may be boring you right now. There's not an excuse for being boring. I'm not saying that I'm not being boring. I'm not saying that I am not boring in class. I may well be very boring in class. I'm always excited, but there's just no excuse. I've given lectures where at the end of it, I go and I make a note on the side that says boring. And then I go look at it later on and I say, now why was that boring? I mean, I looked at the class. I thought it was boring as I was doing it. Why was I doing that? There's got to be some better way to do that. That was boring. So, you make the note and you think about it and say, okay, I've got a smarter way. Always hold them responsible for things they should already know. This is a huge one. I don't know the number of times where I've heard somebody, particularly when they take over a new subject, say, I went in on the first day of class and I asked them, you don't know this from the class that you had in blah, blah, blah. And they looked at me like, no, you must know that. That's the foundation of this subject. We can't go on till you know that. And of course, the vast majority of them do know it, and a few of them have some rust, but nobody's willing to get up and say, yeah, I know that. We're responsible for this. The mistake that I've seen made a whole bunch of times is that you back up 3 weeks and cover that stuff again. Now that's an absolutely terrible thing to do, because all the people who are in the high end of the class who know that, and everybody in the middle who know that they should know that, they're now bored out of their gourd. And they still don't know the stuff. So you've lost them for the first 3 weeks, which is the critical engagement time in the course of the class, and you send the message that you're not responsible for things that you've learned elsewhere. the message that, there can be something that's grown dim in your mind, but you can knock the rust off is huge, because that's what we do as engineers. Not everything is in the frontal lobe all the time. In fact, that's one of the really big things I look for between the master's students and the PhD students, is when the PhD student will come up to something and they'll run into it and they say, yeah, I don't quite remember, but I could figure that out. Let's go ahead. And then they'll go home and they'll look at it, pull the book out. Yeah, okay, yeah, I got it. I'm fine. But they have that confidence to do it. And until you have that confidence that it can be a little dim in your mind, but you can backfill that, then you can't really move the frontiers ahead. So you got to begin by holding them responsible, just for self-respect, respecting them in terms of what they already know. And they respond really well to it too. It's actually, I got to admit, it's easier for me because I teach sophomore, junior, senior, and graduate thermo, that if someone says, isentropic efficiencies? Huh? Look at them. I taught you E30. Yeah, yeah, okay. I'll go read the book and I'll come back if I have a question. Say, yeah, sounds good. And it works for them. They want to be respected. Advice, so platitudes to advice. Hit hard the first weekend. Okay? They're primed, they're excited, and you want to get onto their radar in terms of time allocation. Okay? So if it's at all possible, give them some, but it's got to be of value. It really has to be. You cannot waste their time. It must be truly valuable. One of the most valuable things I can think of is knocking the rust off. So for the ME-140 kids, oh boy, do they get a whopper of a project, writing code. Last year's class was the short takeoff vertical landing of the Joint Strike Fighter, doing the propulsion system model for that, writing the code and comparing with numbers that you can get from published data. First weekend of class was due the following Wednesday. But everything they needed to know, they learned in E30. But what did they have to do? They had to get their MATLAB out and figure out how to write the code with the properties, all the device efficiencies in there, which they'd seen in E30, get their group dynamics going, and actually build that model and come back with the numbers, quantitative set of numbers. And in 1 week, they do. And they're latched in and ready to go. But hit them really hard that first weekend. The historical path is not always the best. This is particularly true in thermo. This is one of the big problems with the second law. So if you say thermodynamics to most people, they think second law, ooh, entropy, what was that thing that we had? The problem is that we like to honor the past, and so we tend to teach things historically. If you teach the second law historically, then the statement of the second law is the cyclic integral of dq on t is greater than 0. Okay, so what bothers people about that? Cyclic integral, dq on t, and the d is not a normal d, it's an inexact differential. Inequality, it's not good. The essence of that is that you can't destroy entropy. Entropy, I don't know what entropy is. The essence of that is that energy wants to disperse. If you have some energy somewhere and you release a constraint, it'll go wherever you let it go. That is the second law of thermodynamics. The cyclic integral of dq on t greater than 0 is a way to express that mathematically. This goes to the next part. Teach essence first, then teach rigor. Before you get to, how do you get to the cyclic integral of dq on t greater than 0, tell them what energy is. Tell them that energy wants to disperse. That if I start with all the air in the corner of the room here and I let it go, it's going to disperse throughout the room. Gee, big surprise, it's not going to all jump back into the corner. Right? Get the essence of that first, then work on the formalization. If you don't get the rigor in there, then they won't trust it either. They'll think, I got some artificial watered down version of it. Okay, particularly science and engineering students, they've been getting artificial watered down versions since they were in 8th grade. Okay, so they need to get the real deal, analytical, quantitative, all terms defined precisely. That's what mathematics is for. That's the language of precision for the concepts that you're expressing. But you have to have the concept first. So don't start historically, essence, rigor, and figure out the best possible path. And often the best path in thermo is to start with microscopic information. People understand quantum states. The second law is actually very simple if you start from that point of view. It didn't happen until around 1900. Boltzmann killed himself because he was depressed. He didn't think anybody believed him. Okay, so we go back, well, let's not start there, let's start in 1850. It's a bad thing to do. Enough said. Always admit when you're serving cod liver oil. People know what cod liver oil is? Anybody have cod liver oil when they were a kid? get it fed to them? I did. Okay, so not many people get subjected to this anymore. Cod liver oil is one of those things, this is good for you. Open your mouth and take this spoon of terrible stuff, and they couldn't articulate why it was good for you, but you need it. We do a lot of cod liver oil dishing in education, and sometimes you can't avoid it. I mean, you really want to set up a path where there's this motivating thing. Here, you want this. Okay, this is what you need to be able to do it. But sometimes there's a bunch of that, and you could say it up front, but it's just hard to make that connection. So if you're going to dish cod liver oil, say, okay, the next 2 lectures are things you're going to have to know. And I'm going to give you an assignment so you can see why you know that. But trust me, for 2 lectures, these are things that I got to put in your head, and then I'm going to connect them together. Much better, give them something that connects them up front, and then put it out. But if you're stuck the other way, own up to it first. Students are really generous. They will spot you a couple of cod liver oil lectures as long as you deliver on the back end in terms of why it was useful to them. You will give some dud lectures. Okay, just own that. Absolutely own that. I gave a dud lecture on Monday. No doubt, and it was terrible. Erica didn't come in, did she? Is there anybody from my E30 class here? Hi, Chris. Okay, so I was talking about gas turbine engines. Gas turbine engines are incredibly exciting. Somehow I managed to take all the fun out of it. Now, in part, I was just kind of tired. I was thinking about other stuff. I was behind. There were 6 things that all had to happen at once. And so I'm going through, doing it. And, oh boy, they are not engaging. They are not engaging. They are not engaging. It's a dud. Okay, but keep going. So this goes to the next part down here. Closed loop lectures are a great luxury. Okay, but sometimes you're going to have to go open loop. What I mean by that for you controls types, if you have feedback signals, boy, is it fun. Okay? I have 4 or 5 students in the E30 class that I can look at, and they're just these wonderful sensors inside the class. They're and I follow them as we go around and look at the faces. One of the signs of a dud is that the sensors they either go dark, no signal out, or they go to the logic 0 state. You just did something that's completely disconnected, from this. And usually it is that I did. It's usually not that they missed it, it's that there was some logical jump in there and I'm just not on my game and didn't connect it in a way that immediately fired neurons in their head. So recognize that you will give dud lectures and be okay with it and make a note and come back even harder the next time. So my response on Wednesday was, I'm bringing gas turbine engines to class, damn it. And we're going to pull them apart and we're going to look at the devices because I'm going to get you back onto that TS diagram to where you care. I don't know how I got you off that to begin with, but I don't care. It was a dud. I'm going to let it go. And when you have to go open loop, cover the stuff that you need to do, but then think about what it was. Sometimes it's that the class is tired. Your key sensors are gone. They just are having a tough time. But if you have to go open loop, go open loop. Closed loop is so much more fun. New courses. I just have a couple more. New courses. Don't shy away from developing new courses. Now, take that, in context. I left the National Lab and came here because I wanted to teach. University, teaching, wanted to teach. Okay? But only do one at a time. And this is a serious issue. So the 370 series is moving along now. That's sort of my in development sequence. But I need to go back and start teaching IC engines again because it's a great class and it's applied thermodynamics and the undergrads really love it, but it's got to get restructured. But I just can't do 2 at once, especially big lab intensive things. So if you sort of leave a little part of your mind that's going to have one that rolls along, and I don't mean each quarter. I mean there's one project class that you're thinking about, as sort of your development. That's not a bad thing to do. Time required to get a new class right, my experience, since I've done a number of them now, 3 to 4 years. 3 years is sort of 1 year, it's kind of a 1 over E, 2 1 over E times, 3 decay times, sort of getting things right. It's 3 to 4 years to get it to the point where you really think that you've got it about right. So be in it for the long haul. And the first time you give it, it will not be right, for sure. It may be close, but it will not be right. And you look at it and say, okay, now what was I trying to achieve? Was it the right set of objectives for them? How do I modify that as you go? And be willing to modify. That's the way that you find better solutions as you go. And you're never finished. Know where the students are at and align your course with them. Impedance matching is a huge issue. If you can teach classes where you know the state of the students, it is so much easier to teach effectively, to impedance match with them. That's one of the really nice things about teaching ME 140, is I know the state of the students because they all began to phase lock at E30, and then ME 170, ME 70, then 131A, 131B, and by the time I get them in 140, I know exactly what they're thinking, what frightens them, what's good, what's bad, and how to stretch them, which is the business we're in. We're in the business of stretching them intellectually in the classes. If you can get that, that's tremendous. The classes that are really hard are the ones where you've got to do this broad impedance match, where you're talking to a freshman and you're talking to a graduate student, and they're all over the map, and you're trying to figure, well, if I say it this way, he'll absolutely get it. If I say it this way, it's going to frighten that person. That's really tough. But this is all about impedance matching. So one size does not fit all. And if you can set it up that way to try and narrow the selection, that'd be good. A couple of parting shots. If you don't look forward to going to class, giving the midterm, even grading the final, so we're coming up on finals, and I got a whole bunch of finals I'm going to have to grade, ask yourself why. And listen honestly for the answers. And when I first got here, one of the emeriti walked in my office and he said, okay, I'm going to give you one piece of advice. He says, if you're not having fun, it's your fault. Okay. Apply that to your teaching. If you're not having fun teaching the class, ask yourself why. When I was first teaching ME 140, for some reason I had this notion that despite all this code writing and project stuff and comparison, that we had to have a midterm and a final. Why? Because all classes have midterms and finals, even though the work was really project-based. I mean, that was the core. Their experience was based upon projects. But for some reason, I felt the need to sit them down for 50 minutes and have them do, green pad, back of the book, closed form problems. And I didn't like grading them. I didn't like writing them. And they didn't like taking them. I asked myself, why? Why are you doing that? In fact, it was a silly thing to do. It was some sort of a historical anecdote in my head that said you needed to do that. We got rid of it. It was much more effective once we removed that. Teaching is and should be fun for both the instructor and the students. If for some reason it's not the case, you're doing something wrong and you're the person who gets to fix it. And the students will help you. They will spot you everything you need to make it fun for you as much as for them. That's the only other bit of advice I have. So, that's it. I'll be happy to answer any questions if there are any. Anybody want that cyclic integral of dq on t?
I'm interested in how you incorporate some of these basic fundamentals of the course itself with the clashes that students might experience in the work world. For example, you're talking about the development of perhaps a new different kind of car, like the development of the hybrid car.
Yep.
And then what happens when students go out in the work world and they have this great new idea, but there's resistance or some kind of difficulty in the economic or political scene that doesn't make the implementation of their idea possible?
Oh, yeah, that's huge. So, so at the sophomore level, it's about getting some ideas in play in a quantitative way. At the junior, senior level, it's about, am I getting the real deal and sort of getting the engineer's view. So that would be an issue for the 370 level, the EMS students. And that's where it's okay, we could build a much more efficient plant. I have a code that says it's much more efficient. What's the capital cost going to be? What's the availability of the resource? And at that level, they immediately latch into it. And most of the students who are part of a class like that are also taking classes in MS&E and in civil and environmental engineering. And so they're building that context because they're at the level where if you're going to be in 370B, which is a huge workload, you better want the world of energy, okay, and all the pieces of it. So it very much goes, the blinders have moved out here. Incredibly powerful in that dimension, but the other dimensions are adding too, just because the people are very mature. But you're right that if you come from one of the earlier levels, come out as a straight bachelor's engineer, there'll be some disconnects which you'll have to equilibrate in the business side of, yeah, that's a good idea, but no business model. It doesn't work here, doesn't work there. Some parts of it we can do, some parts of it we can't. Michelle?
Chris, you mentioned that thermodynamics was always easy for you. And in my experience in watching a lot of teaching, often when a subject has been easy for the professor, then he or she often isn't good at teaching it. Because it came to them so naturally, they often forget a lot of the steps that a student might have to think about to understand that material. They never had to go through that. It was just intuitively there for them. But you seem to have made it work for you, that you understood this easily, you love it. If you were to say something to a colleague that has this other problem of understanding it so well they can't explain it to others, what would you urge them to do?
Examples of everything. When we start with the second law, the essence of which is that energy wants to disperse. The way that we start with the second law is I have all the students in the class, okay, sit in chairs with no spaces in between them, and I designate them to be a monotonic solid. Okay, they are all little atoms in a crystal lattice. Then I bring in 9 big balloons, big honking balloons, and say, okay, you are now the Mark I universe. You are a binary solid universe. Okay, the rules of the universe are that energy is conserved. Okay, energy passes by conduction. You can only pass the balloons. There's no throwing. Energy is conserved. You can't pop the balloons. There you go. You can have 0 or 1 unit of energy. You have a balloon or you don't have a balloon, and they're big enough that you can't have 2 of them in your lap. And there are no other rules in the universe. We put all the energy in the universe in the center, in little region A, 9 atoms in the middle at the origin, the Big Bang, origin of the universe. And I say, go. I have somebody count balloons in the middle of it. 9, 8, 7, 6, 5, 4, 3, 2, 4, 3, 2, 1, 4, 2. And we do this little experiment. They're passing balloons around. And we write the numbers down on the board. In fact, Chris back there was my analog to digital converter, since he's a doubly. He was writing the numbers up on the board for E30 this quarter. And then we go back and we look at it. And we look at it, and the energy density fraction eventually becomes uniform across the universe once the energy gets to maximum dispersion. That energy density fraction is, in fact, the temperature of the system. And when it's equal in that center region and the other regions, we're in thermal equilibrium, and the energy is at maximum dispersal. The entropy has been maximized. And then we go back and we calculate all the possible rearrangements that you could have for 9 units of energy in 36 atoms in this tiny little universe, and write S equals K ln omega, which is rigorously Boltzmann's expression for entropy. But we start out from the really simple idea, from an example, that energy disperses. And that's the essence of the second law of thermo. But for all these things, it's just so easy to find an example. I mean, that's what I like about thermo. Everywhere you look, there's thermo, 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 thermo. So, sorry.
My point. You're talking about thermodynamics, something that we all very much like to teach, all of us in the thermal sciences. What about those of us who have to teach convection?
I will note that you teach radiation, which I would teach it in a moment. But would you teach convection?
Excitement to it. There's no device that I can bring up and point out and say, hey, this is something fun to look at and everything. We can bring examples and everything, but you just can't get that excitement that you can get out of, say, teaching thermodynamics. I think we can all get a lot of excitement out of
thermodynamics is easy.
We all know about it.
The only thing I could say, Reggie, so just to be absolutely correct, I actually think convective heat transfer is very cool. My frustration, that was a bad, let that blow by. Oh, that's bad too. Okay. The problem is the frustration with our ability to do it in a scientific way, in a modern engineering sense, which is what we teach. We teach engineering analysis here. We don't teach empiricism, and it's stuck in empiricism. That being said, the really cool stuff about convection is conduction with fluid replacement, right? And the conduction all comes from thermo, from the second law. If I move a unit of energy, if I'm a little pocket of fluid and I stick up against the wall and I'm hot and I move that little unit of energy over here, it gets to disperse more ways in that wall, and then I get blown off, and there's another little parcel that comes in along the wall. So it's much better than just having a whole bunch of layers of me here, 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 here in conduction, and it's exceedingly cool. I told you my humor is terrible. So that part's really good. It's when you get to the law of the wall, y plus, that stuff that we have to do to get to answers that's where I would not dedicate a single class to it at the graduate level, where you're trying to move their minds ahead as you go. I would leave it as where it is in something like 131A, where it's a subsection of you need the answer, this is how you get the answer. And this is the physical motivation, and here's the tools. The tools are empirical. They will remain empirical for some really good reasons, and think about that when you do research. Because if you can move that, oh boy, would it be great. But I would not dedicate an MS level class to it. So, sir.
You mentioned a few strategies that you have for making the loop closed. Do you have other strategies that you have when you feel like you're in an open loop situation? You said you have some signals out there. Is there anything else you do to close that loop?
I'm not nearly as clever as you're giving me credit for. I look for students who naturally send signals, and there are lots of wonderful, generous students, and they send signals different ways. So Nick in the back corner there, he's a head back kind of guy. He's not the yeah, that's good. He's the oh, that's cool. He's doing it right now. So you have to know, and as they get older, the signals are harder. They're more poker faced, but there are signals. There are signals that are out there. Office hours are a great one too. I love office hours. There's nothing quite as much fun as a fellow who finished his PhD now teaches thermo at the Naval Academy. So a professor there. I remember when he was a sophomore taking E30 from me, and walked in my office in office hours one day and said, the second law, and it's about this dispersal of energy. And we could figure out how that works if we do this. And then that means this. And that would mean that we could do that. And if we knew that, we could figure out the best. Oh, that's all there is? Oh, thanks very much. I had said maybe 3 words to this student, but I got to sit there and watch him do it. That was a big feedback that a lot of the stuff had worked. There was a time constant in there, which was a good signal to me. Okay, time constant, how long will it take before they get it? When do I get to pick up that thread and come back to it in a class? When can I use it to help me get to another piece? But I'm not nearly as good actively at figuring out how to do it. The students provide it. They're really generous. So as long as they trust you not to waste their time. Sir?
So do you have some sort of rules when you design problem sets or homework? Is there certain things, do you have to pick working groups, or do you put very difficult problems that essentially open problems, or how does that change maybe through that?
Oh, wonderful question. It all depends upon that level and that secondary objective that you're after. In the E30 world, you must have a book, because the students will listen to what you say, but then they're going to read along. They need something to pull off the shelf. They need that comfort. They need many examples, way more than you can possibly give in lecture or you can give in tutorials. But you have to engage them sort of at 6 hours a week and on the concepts and feedback. I typically give them problems where they have half the answers to them. And originally they think, oh, yo, what a nice guy. He's giving me problems where I got half the answers, for half the problems. I got the answers to it. And then they realize after a few weeks, those are the ones I spend all the time on. Because I get to the answer and I look at it and it's wrong. And I go back and I smile at them. Say, yeah, but you give me points for it anyway. Yeah, because I want you to learn thermo. And we still have a midterm, we still have a final. 40 points are fine, that's ballast as you go. But that's sort of the sophomore level and highly supported by a book, and you got to bound yourself. Oh, there's more exciting things I could teach you, but they're not ready. They need to get the basic stuff. The junior, senior level, by contrast, you give them the sophomore version of that, they're disengaged, they're out of there. You're wasting my time. Yeah, well, it's easy, but I like my other class better because it intellectually engages them. For them, it's the, oh God, I'm going to be writing hundreds of lines of MATLAB code for this thing. Yeah, you're ready. Let's do it. But you also better give them a problem that's worth their spending 15 hours in a group of 4. This is a 5-unit ME class. It's serious work for this thing, but it's serious payoff. But the payoff happens at that level. For the graduate level class, like the 370B class, then things really do have to come from the outside world, require serious cross connections, and filling in all the interstitial regions that say, well, I think in principle I could do it, but I don't know this. That becomes what we want to teach in lecture, is to fill that in, to show them how that gets filled in so that later on they will fill it in. In fact, the class afterwards is you pick your own problem, you fill it in. You do the whole thing, all the pieces that you need in order to do it quantitatively. So at each level it goes, but don't cross levels. So it's really tempting to say you should do this hard real world project thing for sophomores. They won't do it. They'll do it in some artificial way where they kind of get through to the end of it, but I don't quite know what I was doing, but I got there. And so it's an impedance match again. And it's not easy. Robin.
One last one. You've had the ultimate humility lesson, which is to teach a course for which you also taught the prerequisite. And therefore, you can't blame your colleagues for not teaching the material. And you identified that they need to knock the rust off some things, and that they don't bring things forward well. And that turns out to be a really big deal in teaching. So one way you address it is to have this big project in the first week that really gets them having to go back and grab that information. I guess my question is, how concretely do you identify this is the stuff they need to bring forward, or is it, how does that work? I mean, and how much do the students know about what you're doing?
Okay, so there's a bunch of pieces to that. Because I know where the whole curriculum flows, I know where they should be, right? And so it's not really hard to figure out what the appropriate challenge is. I will pick something that I specifically know connects back to their previous thermo experience, because that's the rust I want knocked off. It's not that they've forgotten it, it's that it's gone off into other corners, it's morphed in some funny ways, a bunch of things have grown dim and the rest. And so you hit hard with something that connects back to that earlier class, but where you can draw on all the other pieces between it. There's another piece to it too, and that's the walk up to you after class or walk up to you in office hours and I don't get it. Well, what don't you get? Well, I just don't get that efficiency thing. Well, what have you looked at? Do you remember back to when we did this in E30? So did you read through the sections in the book? There's a really good discussion of that. And typically when I give the assignment, see chapter 8 in the text that you all have when you had E30. And what it does is it's starchy enough that they don't want to come in and do that. And so they'll come in when they have a real problem, which is, okay, I looked at this, now this is the thing I don't get. Oh, that's great, yeah, that's really hard. Then you jump all over that. But then the word kind of goes back to the rest of the class. Okay, you look at your stuff first, then if you're stuck, go talk to him. And he'll be really nice, but don't go in there if you haven't done it first. And then after a year or so, the next year's class, you're going to get this assignment the first week. Oh boy, and don't go in asking him to do it for you. It's going to be tough, but you'll get it. And so it becomes elliptical in the mathematical sense, that it pushes back each year. And the hope is that this pushes back all the way through the curriculum, okay? So that the people in 131B see 140 coming. And so they're listening to that compressible flow supersonic stuff, because that's coming my way. We're actually going to be building those nozzles in the lab, and I better know that. I'm going to get that now, because he's going to get me on that later. And when they first run into MATLAB, someone said, you're going to write MATLAB up the wazoo when you're in 140. Okay, MATLAB, I'm good at it. So you try to be elliptical, but nothing more clever.
Well, Chris had let me know he has office hours at 1. He doesn't want to be late, so please join me in thanking him so much for a wonderful presentation.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.